This demo aims to showcase the inductive position sensing concept in a very easy to understand and animated fashion. On the left-hand side here, we'll be able to see a 3D representation of the inductive sensor, which is basically a PCB on the bottom and a metal target on top. And the geometric midpoint of this metal target is the position that we're sensing. In here, we support both the linear configuration of the sensor design as well as the radial configuration of the sensor design. And by using this slider tool on the bottom, we can change the location of the metal target with respect to the sensor on the bottom. And that's exactly what we're figuring out later. For linear mode, as we drag through this x-axis, we'll see that the metal target goes from left to right. The goal of this concept demo is really to demystify inductive position sensing. How does it work, and how is it different compared to other solutions out there, such as the resistive position sensing, Hall effect position sensing, and maybe even capacitive position sensing. Inductive position sensors are unique in their own ways that they almost act like transformers. So the presence of the metal target we introduce here basically becomes a disturbance between the magnetic coupling between the primary side of the transformer to the secondary side of the transformer. And the output of the second transformer is what we're going to take in to our sensor IC. By manipulating the energy absorbance by the metal target in the transformer system, we will be able to figure out the position of that disturbance. And this is due to the unique sensor design and the transformer design that we implement in the PCB. Once we figure out the position of the disturbance relative to the length or the shape of the sensor, we'll be able to essentially figure out the position of the metal target. This is a really neat concept, and this is a really effective and powerful tool to measure metal presence on an inductive coupling of transformer system. In the middle here, if you're wondering what these signals are, these are the actual analog signals that we use to measure the position of the metal target. As we mentioned before, the output of the transformers will be fed into the IC, and these are the post-processed signals that we have before the 4 megahertz oscillation due to the excitation voltage from the transformer output. And in the sensor IC, such as the LX3301 or 3302, we have a demodulator tool so that we'll be able to peak detect the amplitude of this transformer oscillation output. So this is essentially amplitude modulated signal. And we use that signal to calculate the position of the metal target. On the right-hand side here, we have the simplified sensor equations. These are the mathematical tools that we use to model and calculate the position of the sensor. And of course, these are very simplified mathematical equations so that we can just get a hold of what it means and for each analog channel, as well as different parameters that we need to take into consideration. And finally, the position calculation. The sinusoids are bounded by different factors in the transformer model. We have, first of all, we have the primary turn number and the secondary turn number of the transformers, which affects the amplitude that we have on the output end of the transformer. We also have KZ, which is the coupling factor due to the air gap that we are setting on our sensor. So if we change the Z-axis on the position sensor by moving the metal target either away from the sensor or closer to the sensor, our model here gives us that the coupling factor decreases or increases in value that would affect the amplitude of the analog signal we get at the end. And VP is the excitation voltage amplitude at the input level in the transformer. AS and AP, these are an important factor. This is the area of the shadow covered by the metal target on top of the PCB. The sine and cosines are the unique signatures of the analog signals we get from our coil design. The geometry of the coil design will affect the mathematical representation of these two signature equations that we use to basically identify the position later in the calculation. As we mentioned, the coupling factor is modeled after a regression model that we found using the data that we collected by using exponential regression. We found this regression constant, and we're modeling it so that the z, which represents the air gap, the z-axis between the metal target and the PCB, affects the result of the coupling factor. And finally, the position calculation is done through a basic arctank function of the ratio between the sinusoids. And this is done through, first of all, it's important to realize that in order to accurately calculate the position, we need to set the two signals here in firmware, post-ADC, and virtual ground for both signals, so that we can extrapolate the quadrant information based on the location of the zeros and the negative numbers and the positive numbers, so that we can figure out the location of that sensor signal. Because without the quadrant information, the location that we align here between the two red dots at this location will essentially be the same as some other locations that we have, let's just say right here, because the ratio between the two signals will essentially be the same. If we don't have that quadrant information, we won't be able to tell in distinct which location that we're getting at the output end. So it's important to know that we need to set a virtual ground in firmware. The final thing I wanted you to notice is that as we change the air gap, we note that the position calculation does not really change. And you're wondering if by changing the red dots on the system, the amplitude is certainly changing, then why does the position not change? This is because we're taking the ratio between the two signals, and these two signals are increasing and decreasing at the same amplitude, at the same rate based on the sensor. So these are the common mode signals essentially. So that our design gives us the immunity to coupling factor, the air gap factor, when we are calculating the final position. One very important observation we can also make here is that by increasing the air gap, our resolution is lost due to a lower dynamic range of the voltage swing for both signals. In order to preserve the resolution, in the chip design, we implement an air gap compensation method by introducing the automatic gain control loop, so that as we change the air gap to a higher value, as we have a much bigger air gap, we compensate dynamically the excitation voltage, so we basically will have a maximum voltage swing for both analog channels to preserve our pristine resolution that we use to calculate the position, which is very important for us in many of the potential applications. And this concludes the inductive position sensing concept demo. I hope you learned just a little bit more about inductive position sensing, or just position sensing in general. I hope you can explore some of the product lines that we offer at Microchip to empower your next embedded systems project. Thank you very much.